maybe also.
Okay, welcome everyone to this next seminar in the One Word Approximate Bayesian Inference series. Today's speaker is Ayush Bharti. We're very happy that you're here to give your talk. He's an academic research fellow currently based in Helsinki, Finland, and is associated with the Department of Computer Science. And the title of his talk is Cost-Aware Simulation-Based Inference, which I think is a very, very interesting topic. And Ayush, were you about to ask me something before I started?
No, no, it's fine.
It's all fun. Okay, so as I said, feel free to put your questions in the chat. I'll pick them when appropriate. And Ayush, feel free to share your slides. And thanks a lot again for accepting to give this talk.
Okay, yeah, thank you so much for the invitation, and I hope you guys can see the slides.
Yep.
Okay, so yeah, thanks again. So today I'll be talking about this recent work on cost-aware simulation-based inference. It was just accepted at AI Stats 2025, so this year. And this is with my collaborators. So there's Daolang is a PhD student of Samuel Kaski in Aalto University in Helsinki, and then also my collaborator from UCL, FX Briol. Okay, so then let's just get right to it. So I'm going to start by like an applied problem, something that I was working on during my PhD, and that sort of is the motivation, or at least the idea or the problem came up while I was working, doing my PhD on these sort of models. So consider that you are, using some wireless communications system. So you have some transmitter, which could be your Wi-Fi router, and then you have some receiver, which could be a laptop or your phone, and then you are in some environment, maybe your home, something like that. So what happens is the transmitter transmits some signal x of t, which then the receiver receives it. So there might be, if there is no obstruction between the transmitter and receiver, there might be like some line of sight path that arrives the fastest and with the highest amount of amplitude or power in the signal. And then there might be some reflections of the roof or the chair or the tables and so on and so forth. And then at the receiver, there's like a superposition of a lot of different signals that arrive, slightly delayed depending upon the time that they take, and then also with different magnitudes depending upon how many, how many times they bounced around in the room. So the job for communication system engineers is to basically account for all of these effects that any environment can bring about. For instance, you can imagine if you are in a very small room, there might be a lot of reflections back and forth of the signal, and then there'll be a lot of signals that arrive, for long periods of time, at the receiver. Whereas if you are in open spaces and then you are connecting to your GPS, then probably there's just one line of sight path that arrives, and there's none of these, multipath propagation. So the job for the communication engineers is to design receivers such that they are able to extract this x of t back from this y of t as nicely as possible. And for that, they need to account for all the effects and modifications that the environment can bring. And this environment in which communication is taking place is called the radio channel. So one way they do this is by modeling it like a linear system. So you have some input that goes into this radio channel, which is basically the entire environment. And then you have this output y of t. And then the quantity of interest that they're after is this modeling this h of t, which is the impulse response, or if you take a Fourier transform of that, that becomes the transfer function. Okay, so assuming that there's this multiple paths that are arriving at the receiver, so you can model it as a sum of different paths L. They all have their different gains or amplitudes alpha, and then they are all delayed by this slight time delay called tau. So each of them, when they arrive, they have a tau and an alpha associated with it, which is the time and the amplitude that they arrived at. And so the y of t is just, if you assume linear time invariance, it's just a convolution of h and x. And then there's some additive wide Gaussian noise, which is added here. All right. So yeah, that's the setting, which is kind of repeated here. So now an example of a model would be a model for, how alpha and these taus are distributed. So the simplest one we can think of is that tau is a Poisson point process, like a one-dimensional Poisson point process with some arrival rate lambda. And then the gains condition on, the alphas, which is the amplitude condition on the delays. They are complex Gaussian with zero mean, and then a variance which sort of starts at this Q, but then it exponentially decays because that's what happens, right? The more the signal bounces around in your room, the exponentially the power decays. So the parameters of this model, for instance, are this arrival rate lambda, and then there's two parameters that affect the variance of the amplitude. So there's the decay rate gamma, there's this Q, the starting point, and then there's also the noise variance that you might see, which is like the measurement noise because you're also measuring these things. And so now if I then try to plot this y of t by simulating like this, and then taking average over multiple 100 different y's, you see something like this, so like an average behavior. So this sigma squared w, which is like this noise floor, which is the variance here. This gamma affects, the how quickly this rate decays. And now you can see this is in dB scale, so this is log, which means so this should be an exponential decay, but in log it's a linear decay. And then Q is, let's say, somewhere around here, which is like minus 80 dB or something like that. And then this lambda also somehow affects, let's say, the decay rate and how many points that you see, how peaky this thing looks. All right, so these are the four parameters of this particular model. Now, if you want to do inference of this model using these data that I kind of showed you, at least the simulated ones, what we'll do is classically we would want to estimate theta given this data, and then if we are frequentist, we would maximize the likelihood of this model. If we're Bayesian, then we'll sample from the posterior, which also is proportional to the likelihood. However, since we are in this seminar talk, so we won't have access to this likelihood function, which is what happens when for most of the simulators, and also for this particular model that I just talked about. Now, the reason is that in this particular case, is that the variables that are important for model description are unobserved. So these alphas and taus that we were talking about, if had we observed that instead of this y of t, then the whole model is, you can write down the likelihood. It's a complex Gaussian likelihood for alpha, and then tau is just a Poisson point process. So you basically have the likelihood. But since we don't observe it, and we only observe this kind of a superposition or this convolution of the different signals, which is why it's not that straightforward to just write down the likelihood. Okay, so that's why we use, of course, these SBI methods. And well, it's not a surprise for people here that this kind of a phenomena or these kind of models are everywhere, from population genetics, where the ABC, the field where ABC kind of began, to now astrophysics, epidemiology, neurosciences, and so on. So it happens in many fields of science and engineering. So the rest of this talk is basically an overview of the SBI methods that people use in order to solve these kind of problems. And then I'll focus in on one particular challenge when you're trying to use SBI methods, which is this computational aspect. And then we'll talk about, let's say, the method of cost-aware sampling, which is basically the meat of this talk. All right. Any questions so far in the chat? I guess not.
No.
Okay.
Nothing so far.
Cool. All right. Then let's continue. Now, this part is going to be, for this particular audience, going to be a bit more quicker. So I hope, but I'll still go through it in case there's somebody, I guess, not familiar with at least the notation that I'm using and so on. So SBI, as we all know, is, there's tons of different methods. And at least I use SBI as the umbrella term for all these approximate inference methods for intractable models, like ABC and minimum distance estimation, which is like a frequentist version of ABC. Indirect inference, where you do inference over, like a related model. Synthetic likelihood, which is when then you assume that these statistics are kind of jointly Gaussian. Or then now we have these neural posterior likelihood and ratio estimation methods, where you learn these conditional density estimators to approximate these different quantities. And then the neural likelihood is like a generalization of the synthetic likelihood method, at least, where now you're not restricted to the Gaussian family, right? You can train any conditional density. So one common feature for all these methods is that you should be able to simulate from your model, which is this P of theta. And then X is what I will use to denote the simulated data, and Y was the observed data. So like a very overview of all of these methods, the only thing common that I can think of is that you're going to sample from the prior for all of these methods. You're going to put these priors into the simulator, you get some simulated data X's, and then all of these go into your whatever is your favorite SBI method, and then the data also goes in, and then out comes some approximate posterior, right? Again, I won't go too much into details of the ABC. This is just a basic rejection ABC step. You simulate, sample theta, simulate X, and then compute a distance. If it's small enough, then you accept it. Otherwise, you reject, and so on. Yeah. And then for neural posterior estimation, you do exactly the same two steps. You sample from the prior, you simulate data. Now this becomes your training data, which is a bunch of thetas and x's and the corresponding x's. And then you try to learn an approximate map, which is a map from X to the posterior directly using some conditional density estimators like normalizing flows. And this conditional density estimator is what we denoted as Q of phi, where phi are the parameters of this normalizing flow, for instance. And so, once this is trained, by minimizing this sort of a loss, which is the log likelihood loss of this normalizing flow, this loss is the expected loss. Expectation is taken with respect to samples from the simulator and, of course, the samples from the prior. And once the training is done, you can just pass like your observed data, which is Y, through this trained network, and then out comes an approximation to the posterior. So everything is kind of amortized, so that's nice. However, here you can see that to estimate the loss, I need to estimate these expectations, right, which are these integrals. And we'll use some Monte Carlo estimators to do that, which is great. But unless, if you have a lot of samples, then that's fine. But if sampling, from the simulator is a bit of costly, then you run into problems. Then, you don't want to use that many data set. If you don't have that much data set, then of course your posterior inference quality will go down and so on and so forth. So anyway, this is basically the computationally costly part. The training itself, we at least in SBI, we don't really assume, because the kind of models we'll be dealing with will be a bit more computationally expensive. So training, which is usually done once, it's not going to be that computationally expensive as compared to sampling. Neural likelihood estimation is very much the same, just that now the mapping is from theta to the likelihood. And so now we use the reverse, you change the context and the target to X and theta, and then now you get an approximation to the likelihood using normalizing flows. The loss again is the log likelihood loss. Expectations are also the same. Okay. So similar computational costly step, which is to approximate this integral. And of course, unlike NPE, here you need to do MCMC to get the posterior. But anyway, you don't have to retrain it again, at least. Cool. So I doubt that there might be any questions for this part either. So if that's true, maybe I can go to the computational challenge.
Yes.
Yeah, cool. Okay, so as I was saying, that the SBI methods rely on repeatedly sampling from the simulators. But if the simulator is costly to run, then you sort of are constrained by the amount of data that you can have, right? This is not something that I thought of. This has been a problem in this community for, since its inception. People have used a bunch of different techniques, which we try to summarize into, let's say, 3 categories. It doesn't need to be this summarization, but that's how we view it. So the first category is the methods that try to reduce the number of calls to the simulator, so number of parameters. So if you have fewer number of parameters, that means you need to run fewer number of simulations. This can be done using like sequential training techniques, like in SNL, sequential NP, sequential NRE, and so on, or sequential Monte Carlo, which is SMC ABC type of methods. But you could also use, let's say, Bayesian optimization in order to, minimize the distance between your observed data and your simulated data. And then this Bayesian optimization will tell you, which next parameter to sample so that, or to run, so that you can minimize this distance. So anyway, so that's, I would say most of the papers sort of fall in this category that we have seen. The second one is where you're trying to minimize how many IID samples you need for each theta from the simulator, right? Because you not necessarily have 1x for each theta, you might, sample a few more. Um, and so there are methods like, instead of IID sampling, people use QNC sampling because that's a lot more efficient. So it covers the space uh, um, more efficiently. So you need fewer samples for similar level of accuracy. You can use, Bayesian quadrature methods to estimate those integrals. So these are just, let's say, more efficient way to estimate integrals by doing some, optimal weighting. Uh, and then the third case is where you use some sort of a side information. To avoid unnecessary simulation. So this could be like these multi-fidelity ABC papers fall in this category where you use here side information. I'm considering the low fidelity simulations that you might have. Dennis Prangle has this paper on early stopping ABC. So that's also some, like a side information that you use to stop running, to not run the simulator at all. And in the past, I worked also on these expert in the loop approaches where, you can get some feedback from the expert that will help you, in cutting down the number of simulations that you need. So again, these expert feedback becomes like these additional information. Our method sort of falls under this category where the side information is about the cost, and we'll get to that later. So another thing is, yeah. So surprisingly, so far, these computationally efficient SBI methods have not taken advantage of the fact that in many cases the cost of the simulator is not the same for wherever for each theta, right? So for some it might let's say the cost varies with these parameter value, and that's what we take advantage of in this paper, and I will talk about a bit more. So the reason why I introduced all of that radio propagation example was because this is an instance of exactly this behavior. Here, there's a parameter, this arrival rate of this Poisson point process. The cost of this model grows linearly with this parameter. So this theta is this lambda here. And so this is kind of the cost of this particular model. So you can see it linearly increases as this theta increases. So I'm going to run this little video. It's going to show you three different cases. One where the lambda is very low, one where lambda is in the middle, and one where lambda is, very large. So what's happening is when lambda is very low, you sample fewer points from this point process. That means you need to sample less points from this complex Gaussian, and then the computations needed to construct this, the impulse response or transfer function is fewer. But the minute this increases, the number of points that you're sampling is now way, way more. And so to construct the same time series, the computations needed get more costly. So yeah, that's pretty much the reason why I introduced this problem in the first place. Now, this kind of behavior is not specific to only this simulator. For instance, in epidemiology, you have these SIR models, the susceptibility, infected, and recovery model, where in this particular case, this is like a temporal SIR model. You have two parameters, infection rate and recovery rate. So if the infection rate goes up or the recovery rate goes down or both, then suddenly the model gets stuck in this for loop because you keep running simulations of the population being infected and so on and recovered. So you get more stuck more in the in the simulator in the for loops, depending upon what is the value of these parameters. And as you can see, like it can be what 5 times the difference in cost from, let's say, the cheaper regions to the more costly regions. And so again, there are other examples also. For instance, aircraft or drone design simulators with parameters like number of wings or propellers and so on. So if the drone is a lot more complicated, it'll take a lot more time to simulate such a drone. Or like any sort of graph-based model where there is some parameters that control the number of nodes that are there. And so the more nodes you have, the more things that you would need to simulate. And again, the cost is going to increase. So all of this to basically convince you that there are many simulators in different fields where this property applies, which is that the cost of sampling or cost of running the simulator is not the same no matter where in theta you run the simulator.
Ayush,
Yeah.
sorry, there is a question in the chat that I think it's very much related to what you just said. So the question is about if you could maybe have some example of your head of different costly simulators that require maybe not just seconds, but hours or even days. I think you mentioned something in your paper.
Yeah. So, of course, in paper, we have like certain simulators, like there's a tsunami simulator or simulators from nuclear fusion, like these tokamak reactors. So they have simulators for that. Like just generating one data point takes a day or so, like it takes hours. So, I mean, none of these SBI methods that we have so far is going to help there in that case. But at least if, for instance, for certain parameterization, so for certain theta, if it takes, I don't know, minutes, and for certain it takes hours, then it just makes sense to exploit this, property, right? So was that the question? So were they asking for more examples?
Yeah,
Which,
it was something. I think your answer is perfect.
okay, cool. So yeah, so now that hopefully I've convinced you that this is first of all, an important problem, and the idea that we have, or the side information that we are going to use, is not something which is made up or cooked up. Now we can go into the meat of the method. So I call this section cost-aware sampling and not just cost-aware SBI, because I'm going to introduce this method a bit more generally than just in SBI. So let's say you have any target density pi that you want to sample from. So in the SBI context, it could be prior for NLE and NPE, or it could be the posterior in ABC. And we assume that sampling from this pi is cheap, which is the case for us, but that each sample theta is used for some downstream task, which has some expected cost C of theta. In our case, again, the C of theta is the cost of running the simulator, which we'll use the minute we sample a theta. And so the idea is that to use this information of the cost to guide sampling towards cheaper regions of theta rather than the expensive ones. So in order to do that, we introduce what we call a cost-aware proposal, which is very much related, proportional to this target pi. So it's basically pi, which is your target, divided by some transformation of the cost. So here G is like a strictly positive non-decreasing function that basically penalizes the cost. So if like you could just penalize, you could take G to be the identity function and then it becomes pi theta divided by the cost, or you could make it to the power of, to squared cost or to the power square root of cost and so on. So that's how we construct this cost-aware proposal. Okay. So the first step we want to see is, can we sample from this cost-aware proposal like we were sampling very nicely from our pi, which was, let's say, a prior, right? So it turns out you can do this just using rejection sampling, nothing very complicated. If you're not familiar with rejection sampling, it's very simple. You have some target pi, but you want samples from this pi tilde, right? So what I'll do is I'll sample from this pi, and then I'll accept or reject based on some probability. And so in this case, let's say you're with some probability A of theta. And this probability is basically the density divided by this blue density, which is So the red one is, let's say, this pi tilde, and then the blue one is some constant times your target, which is pi. So as long as you can find an m, which is some constant, such that this condition holds, you can sort of cover this, the density that you want to sample from, and then you sample from this blue density, and then you accept or reject, based on this divided by this ratio, right? And then you will kind of reject all of these samples. You're going to accept these samples. Okay. Now, what is this acceptance probability in our case? So it turns out if we just assume that g of the minimum of g of c theta is some non-zero quantity, which is fairly straightforward to assume because cost is going to be kind of non-zero, sorry, non-negative, and g is just some non-decreasing penalty function. So this g min, if it's greater than zero, then we can show that this pi tilde is also a density, and that the acceptance probability just depends on this g min value divided by gc theta. All right. So the good thing is that since sampling from this pi is very cheap, there is because pi is just like a uniform Gaussian or something like that, which is our prior in SBI case. So this is not a computationally costly step at all. And so let's look at some examples. So here I'm taking this illustrative example of a gamma distribution. So if you look at this gamma distribution where the first parameter, which I forget, which is the shape or the scale, I cannot remember. If you vary that, the number of uniform random variables that you need also increases depending upon this parameter value. So, if you do this R-Hens-Dieter implementation of this gamma sampler, it's going to vary with, this theta, the first parameter. It's going to vary linearly. And so we use this to illustrate, the different densities. So now if I place a uniform prior, which is this dotted red line, on theta, if I take the penalty function to be, not doing anything, just the identity function, then you get a cost-aware proposal density, which looks like this orange curve. So as you can see, this is the cheap region, this is the expensive region. So it's going to, it's placing more mass here, less mass there. And as you increase the penalty on the cost, you're kind of severely punishing, high cost regions. Like you definitely don't want to sample here, right? And so here is the acceptance probability for the same. And as you can see, the acceptance probability kind of goes lower and lower as the penalty increases. Again, this is not really a problem because we are only sampling from very standard distributions here. So even if I need to sample millions and millions in order to get samples from this pi tilde, it's still very, very quick. Yeah, even if I want to do a lot of penalty, like cost to the power 3 or something. All right. So that's related to just sampling from this. And I see that there's some questions, so maybe we can just take it before moving on. Sorry, you're muted.
Would you like me to read it? So there is a question by Sophia. Cheaper can also mean easier or more popular as a task. Would it cause the model to be biased or low generalized?
Easier in what sense? So here, of course, I when I say cost here, I just mean the time it takes. But yes, it could be something else. Like it could be the amount of money that you burn while running the simulator, right? Well, so you said something about the bias. Wait, let me just try to.
Yeah, maybe it's better if you want to read it yourself.
Cheaper can also mean easier or more popular, let's say tasks. Wouldn't it cause the model to be biased slash? You mean like if we sample from the cheaper regions, then we are kind of biasing our sampling, right? Yes, yes, that is true. And that is where the next part is how we kind of tackle that, if that's your question.
In fact, we can specify the question maybe in a different way in the discussion afterwards if something is
Yes,
unclear.
yes.
Absolutely. And then there is a question by Rui.
Yeah, so how would you obtain such a cost function prior to running the simulations? So this, to estimate the cost function is much easier because you just need to run it I mean, you can sample from the simulator, right? We are anyway sampling from the simulator. You just need to, measure the cost for a different thetas and then just, fit any polynomial or Gaussian process model, to estimate it. So we basically estimate it. The, the short answer is that we estimate it. Estimating the cost is much more, like it does not take a lot of samples, as we'll see later on. Because in the previous example also we saw there's 4 parameters, only one of them actually affects the cost. So you don't really need to fit a 4-dimensional regression model, right? You just need to estimate that linear function. And as long as, and you don't even need to estimate it very, very accurately. It's just the relative trend is what matters. The amplitude does not really matter because, yeah, we are anyway normalizing our cost aware proposal, right? All right, cool. So now, if Sophia's question is how do we correct for the bias, that's where we use self-normalized importance sampling, because now again, we changed our sampling target from pi to pi tilde, which means our posterior is going to be, conditioned on or proportional to pi tilde now. So in order to correct for that, we use importance sampling. So in importance sampling, the weight is, target divided by the proposal. In this case, that just turns out to be, GC theta, which is just, the evaluation of the cost and the penalty function, because pi gets cancelled. B is just some, normalization constant. Since we don't want to find this B, which is this normalization constant, we can use self-normalized importance sampling, which is basically this. You divide by the sum of all these, the weights. So how to use the self-normalized importance sampling? So let's say if you are interested in this kind of expectation of with respect to pi of some function f, then the self-normalized importance sampling would be the weights times this f, where these weights now come from, your proposal instead of, your pi. So yeah, that's basically the method. Here, the only thing that I want to tell you is that we analyzed, the bounds for the weights and the variance of our estimator. And so long as G min and G max are sort of bounded, these things do not have infinite variance. And as you can see here, this is the variance of the Monte Carlo estimator, that we are at worst G max by G min less efficient than Monte Carlo. And of course, you can, since we control G, this is something that you can choose. So things are the take home message from this slide is the estimator is not going to explode with infinite variance. All right, but there is some sort of a cost versus efficiency trade-off here, right? And so let's say we measure the efficiency in terms of effective sample size, which is quite standard in importance sampling literature. So given these self-normalized weights, you can compute the effective sample size like this. Okay. The bounds, we can easily show that the effective sample size is also bounded by this Gmin and Gmax ratios. Again, assuming that Gmin is greater than 0 and Gmax, does not go to infinity. And so in order for efficiency to go up, what you want is, the lower bound to increase, right? Which is you need to maximize Gmin by Gmax. So if I want the most efficient estimator, I want to pick a G such that Gmin by Gmax is the largest to maximized. However, that does not take into the cost, which is what we are after here. So to that end, we introduce the notion of computational gain, which we define it as, let's say, the average cost, expected cost, when using the prior, for instance, in NPE or the target density, versus divided by, when you use our cost-aware proposal. So when you do that, it just means that if you have a computational gain of 2, it means that our cost-aware proposal took half the time than using, let's say, the target density or the prior. So the worst that we can do in terms of computational gain is just be equal to this. So that's why it's lower bounded by 1. So that would be equivalent to just picking pi as our proposal. And then this is upper bounded by G max by G min, which is like the opposite ratio. So now here, if we want to maximize computational gain, you would have to minimize Gmin by Gmax, which is exactly the opposite of what you would do if you were just focusing on efficiency. So there's clearly like a trade-off between trying to go for efficiency and then reducing the cost. Okay. Having said that, then how do we pick the penalty function in the first place? So what we propose, we have two recommendations. The first one is based on these two metrics that I just talked about, that select a G such that the computational gain times effective sample size is close to 1. So ESS is going to be 1 for the standard SBI methods. If you just use prior, it's going to be 1 computational gain. So it's 1 for just the normal SBI method. So what we want is maybe slightly lower ESS than 1, but then slightly higher computational gain. And so that if you multiply them, it's close to 1, you get some reasonable results. You get some, you don't compromise too much on efficiency, but at the same time you get some computational gain as well. So that's recommendation number 1. Recommendation number 2 is born out of this problem that what if the actual posterior lies in the expensive region? Then you will definitely not have a lot of samples from there, right? And of course, we'll do this importance sampling trick, but that might still not be, you might still be losing out on some efficiency there in those cases. So for that, we recommend using what is called multiple importance sampling. So instead of taking one proposal distribution, we take a bunch of J importance distributions. And then the final estimator is like an average over these J estimators. And so our recommendation is that one of these components of these J importance distribution can actually be your prior, so that you actually cover all the spaces that you think you want to cover. At least if, for instance, there are 4 components, 1/4 of the samples will come from the prior. One component can be based on this CG times ESS metric. So you pick a G such that this is close to 1. And then we recommend that maybe add 1 or 2 components with slightly more penalty, so more stronger powers of G, for instance, such that you get more computational gain also, right? Because it's not just yeah, if that's our goal, to reduce the cost. So in the end, the cost aware SBI method boils down to this. So this was the standard one: sample from the prior, run the simulator, and feed it into your SBI method. Now you take your prior. We first have a rejection sampler that I talked about. And then you get samples from the cost aware proposal. You have the cost function that we estimate, G that we pick. And then using these two, we can compute our weights. And yeah, and just feed that into your SBI method, and that's it. Now, the good thing is the ESS, the effective sample size, the computational gain, the weights, everything, none of these estimation or computation requires running the simulator at all. So you can do all of these like beforehand, pick a G, and then start your, running the simulator and so on. So it's not like you need to run simulator in order to, find a good G or something. All right. So that's the
Oh,
overall.
we have a couple of questions. Perhaps maybe you
Yeah,
want to
so just after
address
this
them.
slide, there's going to be a break before the results. So maybe we
Oh,
can,
okay, great.
yeah. Okay, so in the end, the cost aware NPE is exactly the same loss function that we had before. You just add, these uh, importance weights in the beginning. Same with NLE, and then you do the normal ABC using our cost aware proposal, and then in the end, you just construct the posterior like this, which is a weighted sum of the accepted samples. So basically, implementing this is super easy, because all of these weights are just G times C theta, G of C theta, that's it. Okay, now we can go through the questions perhaps. Maybe I can just go it myself.
Yeah, thanks a lot.
Okay, so Dan says, if the normalized importance sampling applied to each training batch. Well, I guess your question should be here. So yes, yes, you would. Typically, the batch is small, which might lead to very biased weights. You ever noticed or having comparable magnitudes ensure the stability? If the weights can be please. Yes, so the weights can be pre-computed. So I guess that answers your question maybe. Uh, Imagine you have some simulation that is rare to obtain and it is some hard case. For example, for primary infectious rate is high and recovery rate is low, and the cost of simulating it is much higher, then you will sample less of this kind of simulations and the SBI model will not perform well for these while potentially overfit for easy cases. Uh, not not necessarily. So that is why we are correcting using these weights, right? So the weights is supposed to take care of that. I will, do I have that result? I will show you. Okay, I'll talk about this in the results, which one is easy case and which one is a slightly hard case. But what you just said is exactly why we use importance sampling. Because imagine if your posterior lies in the, you know, the hard case, then you might not have enough samples from it, but you can still adjust for it using these weights, right? That's the whole point. How do you choose the number J? This is more of a heuristic. So as our recommendation was that you include at least the prior there, you include something from CG times ESS, and then it's up to you how many, how many additional components or importance distributions you want to add, depending on how much gain you want to get. So if you include J to be like 10, that means only 1/10 of the sample comes from the prior, right? So if your posterior you think should lie in the high cost region, then maybe you might lose out on efficiency there. So it's sort of like the trade-off. However, on the other hand, if your posterior lies in the low cost region, you actually don't have to use this importance sampling. You can just use a high penalty. It's going to sample much more from there, and your posterior is going to look much better, automatically. Okay, so that's pretty much it. So, how am I doing on time now?
Oh, pretty well. I mean,
Okay.
there's a 15 minutes. Well,
Okay.
no, I mean, in terms of time, let's say 5 more minutes. Sorry, 5 more
Okay. Five
minutes.
more minutes.
Yeah, yeah.
Okay. So yeah, that should be more than enough. So let's look at this. This is the ABC. So we used ABC on this gamma simulator that I talked about before. So the first thing what we do is if you increase the number of samples in ABC, in this rejection ABC, of course the cost increases, right? Um, this red line is the cost from sampling from the prior. As you increase the penalty here, from to the power 1 to square to cube, the cost that you incur is less. It's pretty obvious now. And then now here we also add this multiple importance sampling thing, which is sort of slight, near this guy, the orange one. And so here we took three cases, one where the true theta lies in the low cost region, in sort of the middle region, and then in the high cost region. And so for ABC, you see, we don't really lose out much. The red points are, so this is the efficiency, it measures efficiency, how good is your posterior, and this is the cost. So you want to be kind of, somewhere here, right, in the bottom. So no, yes, low cost and low MMD. So the red ones are here if you just use your prior. The minute you use any of these, either the multiple importance sampling or, G equals to Z, you start to see that it actually improves on MMD also, and also, you save, well, in this case, it looks like maybe like 35, 40% of cost. When you increase the penalty more, what's happening is the number of accepted samples becomes much smaller. So the variance in your, posterior over different runs increases. So sometimes it's like very good. Sometimes, maybe it's like a few samples accepted near theta true. Sometimes, it can be far. So of course, you shouldn't penalize, at least in ABC, that badly. But as you can see, the multiple importance sampling seems like a pretty good heuristic in terms of, balancing both. Next is the epidemiology model. So one model I already showed before, which is this two-parameter model. We added two more, which is one of them is this homogeneous SIR. It has just this infection rate parameter that increases sort of linearly. And we use like a GP to fit these. And then there's the Bernoulli SIR model, which has three parameters. And as you can see, one of them the cost increases linearly for these two, but for this one, it kind of goes down exponentially. Uh, so you're going to right off the bat, looking at the cost plot, I can tell you that the gain that we'll get in computation cost is going to be much more for this model, right? Because we're not going to sample a lot from here, but we're going to sample more here, and it saves a lot more cost. So this is the table of results. Again, there's for efficiency, I'm plotting the MMD between the posterior that we get and some reference posterior. And then this is the time saved, which is 1 minus the ratio of the simulation time using our method versus just using the prior. So it should be more. Uh, so these are the three different models. And maybe let's just focus on the multiple cost-aware multiple importance distribution. You can see that we consistently get something like 30, 25 to 30% reduction in cost, whereas the performance is quite similar. In some cases, like for the Bernoulli case, as I told you, for G equals Z square, so squared penalty, I'm saving a lot more cost. And also for the temporal, the first plot that I showed with these heat map, we are saving a lot more cost. Of course, there's going to be some reduction in the performance. But yeah, that's basically the trade-off, right? How much you want to save and get reasonable results. So in this case, we used NPE. And then the last one is this, again, the radio propagation example that I've been talking before. This is slightly more computationally costly. So sampling 10,000 samples from a uniform prior took like 15.5 hours. But using our cost-aware proposal with, let's say, this G equals Z square, it took kind of almost half, like 8.8 hours. But as you can see, the posterior that we get is sort of very similar, right? For the multiple cost-aware method, we actually even see slightly better posterior, at least for this parameter that was controlling the cost. Anyway, so the whole point is you get similar results by saving hours of computational time, right? That's pretty much it for the end. So the one point that I wanted to make here, uh, yeah, so some limitations. It's an important sampling method. So if you are working with, there's many parameters that affect the cost, then it's going to be important sampling in much higher dimensions, which as it's kind of known that it may not work very well. However, you could then use like adaptive importance sampling, sort of slightly more advanced methods in order to do that. You could also do that in order to target like the posterior lying in the high cost region. So for instance, you did a first round of cost aware method with fewer samples, and then you see that the posterior sort of lies in the high cost region. Then you can adapt and sample around there a bit more, right? Uh, yeah, the performance degrades when the true parameter lies in the high cost range, as I said, for NP and NLE, because the conditional density does not see that many training data points there. On the flip side, if the posterior lies in the low cost region, the performance is even better because now you see a lot more samples there. So yeah, that's sort of what happens there. And yeah, you can apply the cost aware thing with your sequential Monte Carlos, your SNLE and SNPE, combine it with QMC points and so on. So it's very complementary because we only affect, like the only thing that we are doing is the prior is what we are changing, right? And then you account for that in the loss function. But there's nothing else that is affected. So you can, it can be, for instance, applied to NRE also in a similar manner, although we didn't do it. The method that the sampling approach is not used is where this would not be applicable, like like Bayesian optimization type of approaches. But then there you can use cost-aware Bayesian optimization, which kind of does similar thing, right? You have a GP over the cost, and then you try to have an acquisition function that is let's say, expected improvement divided by the cost. So we focused mainly on the sampling SBI methods like ABC and NP, NLE, and so on, only because these are the ones that that are used more often. So yeah, that's it. That's it from me.
Thank you so much, Ayush. So a virtual round of applause to you. Very, very nice presentation. I'm going to stop the recording now.